Question 2 says it has two parts actually. It has A and B, and question A has a diagram. It says a 3 kg metal ball is suspended from a rope as a pendulum. If it is released from point A and swings down to point B, the bottom of the arc as shown in the diagram below. So this is the diagram here. Okay, so it is released from this point, point A, and it reaches point B. So since it is released from point A here, we should actually, as a student who takes physics, we should know to say, when you just hear a statement to say release, that means the initial velocity is 0. So which means the velocity at A should be equal to 0, like that. So it swings down up to point B, and as it does that, it is going down a distance of 0.5 meters. So that is the displacement in the vertical axis of 0.5 meters. So they've also given us the mass, say it's 3 kilograms. So what are we going to do? They told us to say we should show that the velocity of the ball is independent of the mass, and to calculate the velocity of the ball at point B. So how are we going to do this? So let's look at question 1 first. Question A1. Since they've said we should show to say the velocity of the ball is independent of the mass, and we know to say friction is not existing here, which means mechanical energy is being conserved. And mechanical energy is just actually the combination of all the energies that are acting on this object. So we have gravitational potential energy and the kinetic energy as on this diagram. Those are the two that we're going to focus on. So since mechanical energy is being conserved, we should make sure to say mechanical energy at the initial point should be equal to mechanical energy at the final point, like that. And this is now what we are going to follow in order for us to solve question 1A. So I'll say uh, question 2A1 like this. We are saying mechanical energy at the initial point should be equal to mechanical energy at the final point. And the mechanical energy is the combination of uh, potential energy, which is PE initial, plus KE, which is kinetic energy at the initial point, being equal to what? PE final, potential energy at the final point, plus KE at the final point. But remember, at the initial point, we said this object is being released. We said V at A is equal to 0. First V at B, this one we don't know, but it has a certain velocity. So since we're saying it's being released, we should understand that uh, the initial kinetic energy doesn't exist. Why? It's because velocity is equal to 0. So that means we can cancel out this guy from our equation. Can cancel out this guy. And also, since it's descending down, we know to say it is going down a displacement of 0.5. So if I look at that distance, I'll say this is 0.5 meters like this. And if I'm calling that the ground, that means here it is 0, and there at the top it is 0.5. So if you look at our diagram, it was a pendulum which was starting from that point going to the initial point, which is 0. So that means at the final point, potential energy also doesn't exist. Twice because the height is equal to 0, and the potential energy is due to height. So I'll say my equation now will become potential energy at the initial point should be equal to the kinetic energy at the final point. And if I do that, I'm going to say potential energy is equal to mgh, and this is equal to what? This is equal to half mv squared, like that. And if I do that, you're going to see that the mass of the ball, m, because they've said we should show to say the kinetic, or I mean we should prove to say the velocity is independent of mass. If we look at the mass of this object now, you can see that m is existing on both sides of our equation. The m of the ball that we have, it is appearing on both sides of the equation, and hence we can cancel it out since it's common. So I'll say my mass leaves that side, and this mass here leaves this side. And what are we going to remain with? We're going to remain with it GH at the initial point being equal to what? Being equal to half V squared, like that. And if that is the equation now that we are remaining, that means we can also simplify it further by multiplying it by 2. That means it cancels out with this one, and the equation will become 2GH will be equal to V squared. This is the V final squared, and this is the initial height, like that. And you can see to say the velocity here, the V final, is just actually equal to this guy. The m has nothing to do with this. So the mass of the ball actually doesn't is not necessary in this equation. Hence, we are proving the equation and to say the velocity of the ball is actually independent of the mass. It does not matter what the mass of this ball is going to be. If it is falling through the same height, the velocity is always going to be the same. And we are proving it in this manner. Okay, so that was question 1A. I mean 2A1. Now we can look at question 2 like this, which was saying we calculate the velocity at B. So what will be the velocity at B? We've already found the expression for the velocity at B, and we've said it's this one. So we're going to say V squared, V final squared will be equal to 2GH, H0, like that. And V squared will be equal to 2 multiplied by the gravity, which is 9.81, multiplied by the height, which is 0.5 meters, like that. So my V will be equal to the square root of these guys, 2 multiplied by 981 multiplied by 0.5, like that. And I'm going to get my V being equal to 3.180 meters per second. That is the final velocity of the ball when it reaches at the point B. Okay, so that was question A, question 2A. And you can watch the next video in order for you to see how to go about question 2B, and subscribe to the channel and also like the video. Thank you.